Hey everyone, we're going to look at number 4 in section 4.6. We're going to find the transition points for this function. So transition points again are anytime we have a local max or a local min, any local extrema, or if we have a point of inflection. Basically, the shape of the graph is changing either from increasing to decreasing, decreasing to increasing, or concave up to concave down, or vice versa. Okay, so we're given a polynomial function, which is nice. The domain is all real numbers. There's no holes or breaks, no points of discontinuity, no vertical asymptote. So it's nice to deal with. Okay, so first of all, we can have transition points at local extrema. So how do we find local extrema? Well, first derivative, right? And we're going to do a sign check, obviously, on the first derivative using the first derivative test to determine if we have indeed local max or local min. So the derivative of 4x cubed is 12x squared. Derivative derivative of 96x squared, bring the 2 down. 2 times 96 is 192 times x. I'm going to factor out a 12x from that, leaves x plus 16. And so our first derivative is 0, obviously, when x is 0 or when x is negative 16. Go ahead and find the second derivative. Derivative of 12x squared is 24x. Derivative of 192x is 192. When is our second derivative equal to 0? Well, that's going to be true when this is true, and that gives us x is negative 8. Okay, so what I would do then is to do a sign check, and potential transition points are 0, negative 16, and negative 8. So in order, I put them on the number line here, and I do a sign check. I've done all my sign checks for the first and second derivatives kind of together. So remember, our first derivative is 0 at negative 16 and at 0. And if I plug in something less than negative 16 into my first derivative, like negative 17, this will be a negative number, this will be a negative number, and a negative times a negative is a positive. If I plug in anything in this interval, like negative 8, I get a negative times a positive, which is negative. So it's negative all the way through there, but I go and put a negative on either side. Again, negative 8, the second derivative is not 0. Sorry, the first derivative is not 0 at negative 8. Second derivative is. And then I plug in a value greater than 0 into the derivative, and it's positive. For the second derivative, as we said, the second derivative is 0 when x is negative 8. If I plug into the second derivative something less than negative 8, like negative 16, this value will be negative. If I plug in something greater than negative 8, like 0, this is positive. And so we have this analysis. Just combining that now, this is not part of the problem, but what is the shape of the graph then? We can see the first derivative is positive, second derivative negative, so we're increasing concave down, we look like that. Minus, minus, decreasing concave down, look like that. Minus, plus, decreasing concave up, and then plus, plus, increasing concave up. And so, if I were to sketch, rough graph, again, this is not exactly perfect, but here's basically what our graph would look like, right? Just grab this piece, put it right there, this section, put it right there, this section, drag it through there, and then that section there. And at negative 16, we see we have a local max because we're going from increasing to decreasing because the derivative changes from positive to negative. And at 0, we have a local min because we're changing from negative to positive, right? Decreasing to increasing with the function y. This is the first derivative test. And at negative 8, we have a change in sign in the second derivative, which means we have a change in concavity, right? We're concave down for everything less than negative 8, concave up for everything greater than negative 8. So indeed, these are all, negative 16, negative 8, and 0 are all transition points, right? Negative 16, we change from increasing to decreasing. At negative 8, we change concavity from concave down to concave up. And at 0, we change from decreasing to increasing. Okay, I hope this helps with this problem.